Hello, this is Brian with Engineering Made Easy. Welcome to our second lesson on thermodynamics. Today we're going to be talking about pressure, kind of a few topics that we need to cover so that we can understand pressure and how it relates to other thermodynamic properties later in the course. So first, let's define pressure. Let's recall that pressure is defined as a force per given unit of area. We covered some common units of pressure in our previous lessons, so be sure to check that out. Some of those are like bar, kilopascals, pascals, etc. We can really think of pressure as being similar to normal stress in a solid, where stress is also measured in force per unit area. And when I think of pressure, one way I visualize it is to think of water in a swimming pool. That fluid in the pool is constantly exerting a force on the walls. That's your pressure. That's your force on the area of the walls. And in general, as we're going to see, our pressure increases with depth in any given fluid. So first, let's talk about gauge pressure versus absolute pressure. There's some definitions we need to know. So the actual pressure, you can think of this as your thermodynamic pressure at any given point in space that we're going to call the absolute pressure. Now think of the absolute pressure as being measured relative to a perfect vacuum. I always think of it as being relative to pressure in space, which is essentially zero. On the other hand, we have gauge pressure, where gauge pressure is the difference between absolute pressure and the atmospheric pressure. So now instead of being relative to a perfect vacuum, we're relative to atmospheric pressure. You can think of gauge pressure as being what you would read on a pressure gauge. That's why it's called the gauge pressure. It's relative to your ambient pressure on Earth. So the distinction I make, absolute pressure is relative to space and gauge pressure is relative to pressure on Earth, atmospheric pressure. For thermodynamic calculations, we are mainly going to be using absolute pressure. Both are practically useful in engineering applications, but for this course, we're mostly going to be sticking with absolute pressure. Now, if you need to convert between the two, here are a couple equations to help you out. The gauge pressure is just equal to the absolute pressure minus the atmospheric pressure. And corollary to that, the absolute pressure is going to be equal to the gauge pressure plus the atmospheric pressure. For standard calculations in the course at sea level, we're just going to take the atmospheric pressure to be equal to 101.325 kPa. And if you need to convert that to other units, you can pretty easily. And then if you ever see pressure given in the course, make the assumption that it's absolute pressure unless it tells you otherwise. That's what we're going to be assuming for all thermodynamic calculations. Now let's talk about pressure versus depth in any fluid. So with any fluid, whether it's air, water, oil, mercury, any fluid, pressure increases linearly with depth. For example, air pressure on Mount Everest is much lower than at sea level because we're farther away from the center of the Earth, and pressure is going to increase with depth in the direction of gravity. Right? We can think about more fluid resting on top of other layers of fluid. It's being pulled down by gravity, essentially gives us more weight, which leads to more pressure. So let's consider this volume of fluid on the right. Essentially, we've got a tank, and the red line represents the top layer of fluid. You can think of this as water in a tank. And if we're considering the pressure at points P1 and P2, the difference in pressure between those 2 points is going to be directly related to the difference in height and the fluid density. So here's our equation down here, delta P, change in pressure, which is equal to pressure at point 2 minus the pressure at point 1, is going to be equal to rho, which is our density, times G, which is our gravity constant, times delta Z in meters, right? So if we know the fluid density, and we know the distance between 2 points, we can calculate the difference in pressure. So if we were to change our point 1 to be the free surface at atmospheric pressure, then we can define our pressure at any point simply as a function of the vertical depth from the free surface, where the free surface is where our fluid is in contact with atmospheric air, right? So if we rearrange that equation from the previous slide and we substitute P atmospheric for P1, we can see that P2 is equal to the atmospheric pressure plus rho times G times H, where we've basically replaced delta Z with height, right? So the height being the difference in vertical depth between the 2 points. Now, key thing to remember here is that even for complex geometries, this basic relationship holds, provided that the points are connected by the same fluid. So if this whole stretch is all water, for example, then points 2, points 3, and point 4 are all going to have the same pressure, because the vertical distance between the atmospheric pressure and the 3 points is the same. And that's all we need to pay attention to as long as they're connected by the same fluid. So this is going to be important when we're looking at, for example, manometers, or if you were designing like a dam, for example, where you had a free surface up here, and then you had fluid passing through a volume, and then you wanted to know the pressure at this point. All you need to know is the vertical depth between the 2 points. So that makes things pretty simple. So those are the big topics we need to cover with pressure. Next time we're going to go through a few examples related to the material that we've covered so far, and then we're going to get into more in-depth topics with thermodynamics. So as always, if you have any questions, leave them in the comments, and thanks for watching.